In order to arrive at the final result for the center of mass of a n particle system in our xyz coordinate system or the Cartesian coordinate system, let us start with first a two particle system. Now when we have just two particles, I can take the line joining those two particles as the x-axis. So you may have a case where the two particles lie along the usual x-axis like this. There is a particle of mass m1 at x coordinate x1 and a particle of mass m2 at a x coordinate x2, and then I may say that the x-axis is this line, and I'll be happy with that because this is how I usually choose my x-axis. But then I may also have a system where there is a mass m1 at some point and a mass m2 at some other point, and they are not along our traditional x-axis, but I can still take the line joining these two particles as the x-axis, and I can still get the same result which I will end up getting here. So it doesn't matter how the masses are placed, as long as there are two masses, they will always lie on the x-axis. And let's say that there is some point C which is the center of mass, and we are interested in finding out where it is. And it can be to the left of these particles, to the right of these particles, or it can be in between the two particles. You can take it anywhere as long as you take care of the signs. So let me take this C point, the center of mass of this two particle system, to be somewhere in between them, and I say that the x coordinate of this point is x. Now when I take care of all the signs and when I solve this problem, if x is less than x1, then I know that the center of mass is to the left of m1. If x is more than x2, then I know that the center of mass is to the right of these two particles. And if x lies between x1 and x2, then I know that the center of mass is indeed in between these two. So no harm in taking this point C anywhere and assuming the x coordinate of this point to be x, and then solving it and then seeing what the sign of x is or what the value of x is. So let us try to figure out the moment of inertia, the first moment of inertia of m1 about this point C. So we have to find out the location of m1 with respect to C. So that will be this wine red line that I'm going to draw. That line will define the location of m1 with respect to C. And there is a green line to show you what is the location of m2 with respect to C. That's the green line, this one. And when I find this vector, let me take a case where we have got a two-dimensional coordinate system so that you will easily follow. If you have got a two-dimensional coordinate system and I want to figure out what is the vector drawn from a particle 1 to another particle 2, where I know the vector drawn from origin to particle 1 like this, I know that this is R1, and I know the vector drawn from origin to particle 2, I know that this guy is R2, and if I want to find out what is that vector which is drawn from 1 towards 2, then I know that I can say that it is R2 minus R1, or final minus initial, isn't it? From 1 to 2, if you draw a vector, the final point of that vector is 2 and the initial point of that is 1. So if I find out what is the location of the final point, that is R2, and from that subtract the location of the initial point R1, I will be able to get that vector. This is trivial knowledge. So here, how do I find out this vector that is drawn from C towards this mass m1? That will be x1 minus x. And how do I find out the vector that is drawn from C towards m2? That will be x2 minus x. So therefore, I can then say moment of m1 about C is going to be m1 times x1 minus x, and the moment of m2 about C is going to be m2 times x2 minus x, and I want the sum of these two moments to be 0. So therefore, according to the definition that we all have agreed upon for the center of mass, m1 times x1 minus x plus m2 times x2 minus x should give you a 0, and that will show you that x will turn out to be m1 x1 plus m2 x2 divided by m1 plus m2. This is what x turns out to be. So it's like a weighted average, and you also know from the section formula that this point then should lie somewhere between m1 and m2. Right, so this is a very simple case. We can make two observations from this. One observation is that for a two particle system, the center of mass lies on the line joining the two particles, somewhere in the line segment between them. Center of mass of a two particle system lies on the line joining the two particles somewhere on the segment joining them. And the second one is use of section formula. So this is something that you've already learned. If you have a point x1 and if you have another point x2, and if you try to divide the line segment joining these two in the ratio of m2 is to m1, then the point that will do so, its x coordinate will be, you know that m2 will go with x2 and m1 will go with x1. So you will have m1 x1 plus m2 x2 divided by m1 plus m2, which is the same answer as what we have got here. So that shows you that the center of mass divides the line joining the two particles in the inverse ratio of these masses. Center of mass divides the line joining the two particles in the inverse ratio of the masses. That implies that the center of mass will be closer to the heavier object. Center of mass will be closer to the heavier object, and this is the second thing that we can know from this result. Now, how can I extend this to a three particle system? Now, to extend this idea to a three particle system, what I will do is I will take a xy plane and I will assume that all these three particles lie in a plane. Of course, the three particles may not lie in the xy plane, they may be randomly spread in space, but then wherever they are, I can always draw a plane that goes through three particles and I can call that plane my xy plane. So what happens for a three particle system? The plane containing them is the xy plane, and the particles are located somewhere in that plane. So here is our xy plane, and the three particles are probably somewhere here. So this is m1, somewhere over there this is m2, somewhere we have m3, and m1 is at some coordinate x1 comma y1, m2 is at some coordinate x2 comma y2, and m3 is at some coordinate x3 comma y3, and their center of mass I am saying is some point which is not the origin, so a more general case, which is this point C that has got coordinates x comma y. Now, I will have to figure out the vectors drawn from C towards these particles. So I will have to figure out probably this R1 vector that I draw from C towards M1. I will have to figure out what is this R2 vector, R3 vector, which I draw from C towards M3, and I will have to figure out what is R2 vector, which I draw from C towards M2. So these three vectors, and I can easily find out these three vectors, and then I'll have to find out the moment of M1 about C, M2 about C, and M3 about C, add them up all, say that it should be equal to 0. So the term that I'm going to finally get is this: M1 times this vector should be the final location minus initial location, so it will be x1 minus xi cap plus y1 minus y j cap, and the second term plus I will get something of the same kind for M2. So the final location minus the initial location will give me x2 minus xi cap and y2 minus yj cap. So you're going to have M2 times x2 minus xi cap plus y2 minus yj cap, plus the third term M3 will be x3 minus xi cap plus y3 minus yj cap, and all that should be equal to 0. And what you can do is you can club up these terms on the left hand side. So you can take m1 x1 here, m2 x2 here, and m3 x3 here, and they will have that I with them. So this will give you m1 x1 plus m2 x2 plus m3 x3 with I, and similarly for the y1, y2, y3 terms, so you will have m1 y1 plus m2 y2 plus m3 y3 with a j, and on the other side you can take these terms. So there will be a minus m1x minus m2x minus m3x. You can take it to the right hand side and everything will become plus. So you will have m1 plus m2 plus m3 times x I cap, and similarly you can take the y terms also. So you will have a y term m1 y with a minus sign here from the first term, and then minus m2 y from the second one, minus m3 y from the third one, and all of them go to the right hand side and they will become m1 plus m2 plus m3 times y j cap, and then you can just try to compare these two equations, and then you will see that x will turn out to be m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3. So I can write, therefore x coordinate of this point C is summation of I going from 1 to n mi xi divided by summation of I going from 1 to n mi. And similarly the y coordinate of this point C will be summation of I going from 1 to n mi yi divided by summation of I going from 1 to n mi, and this will give me the center of mass. And by extension you can see what will happen in a three-dimensional case. So if you had x, y and z coordinates, you will also have a z coordinate of this point C, and the z coordinate of this point C will be summation of I going from 1 to n mi zi divided by summation of I going from 1 to n mi. So you will get the center of mass of any number of particles using this method. So once you do it for a 3-particle system, you can easily extend to n-particle system. So extension to n-particle system is very trivial for an n-particle system. So here for a 3-particle system you should have I is equal to 1 to 3 actually, where I have already extended it to n particles and I have said 1 to n, and so we don't have to really do that formally now. We can then try to extend this to maybe continuous masses. Continuous masses, again it will be the same thing. I can take up a continuous mass and I can break up this continuous mass into small pieces. So there will be those small pieces which each have some mass of delta mi, where that mass in fact turns out to be very close to zero, because I'm going to I'm going to chop it up into small pieces. When I chop it up into small pieces, each piece has a mass that tends to zero. So what I can do is, for this continuous mass system, I can say that the number of pieces or the number of elements will tend to infinity. So that means mass of each element will tend to 0. That means M1 will tend to 0, M2 will tend to 0, and M3 will tend to 0, and so on. And whenever I use integration to solve such a problem, anything that tends to 0, I usually take a dm for that particular term. So I can then say that these terms will look like dm1 into x1 plus dm2 into x2 plus dm3 into x3 and so on, where a general way to write that is integral of x dm. So then the x center of mass, that I have figured out to be summation of I is equal to 1 to n mi xi divided by summation of I is equal to 1 to n mi, can be rewritten as integral of x dm divided by integral of dm. Now you have to keep in mind that it is this mass term which will have a d with it, not the x term, because a small mass, let's say this small chunk here, may have a negligible mass, but it may still have a large x coordinate, a large y coordinate, and so on. So you have to keep in mind this format of the center of mass formula, which is true for continuous objects. And analogously, we can write what happens for the y center of mass. That will turn out to be integral of y dm divided by integral of dm, and the z center of mass, which will turn out to be integral of z dm divided by integral of dm, where the dm is any general particle's mass and z is that general particle's z coordinate. Here again dm is that general particle's mass and y is that general particle's y coordinate, and so on. So this is how you will find out the center of mass of continuous objects.